So let's look then at some specific uncertainty principles. We can go back and look again at the position momentum uncertainty principle. We can formally derive it now without presuming Gaussians or any other specific forms or distributions. We consider the commutator of the momentum operator and x, where we're treating x as the operator for position in this one direction x. And to be sure we're taking the derivatives correctly, we will have the commutator operate on an arbitrary function. So we've got the commutator of px and x operating on f, and we have minus IH bar d by dx from the px operator. So this is px x, and this one comes from x px, and we have it operating on our arbitrary function. And when we do that, we can explicitly multiply these out like this, and taking the derivative with respect to x of this product here gives us two terms, one of which is just f, and the other of which is x d by dx of f, but that cancels out with this term. And so we're left with minus IH bar times f, the function f. Since this function was arbitrary, then we can drop it in both sides here and get this operator equation in this form here. So the operator that corresponds to the commutator of px and x is just minus IH bar, or technically this multiplied by the identity operator. And the commutation rest operator, therefore, is just this number minus h bar, or technically minus h bar times the identity operator. Hence, the average value, the expectation value of this operator for any state is just minus h bar. And in this case, we have an uncertainty principle that is going to apply to any conceivable state of the system. So from our general form of the uncertainty principle, which we wrote like this, then for our position and momentum uncertainty principle in the direction x, we're left with this expression. We can also look at another uncertainty principle, and this one is between time and energy. This is not quite on such sound theoretical ground as some of the others, and we'll see why in a minute, but it does work. The energy operator is the Hamiltonian h, and from Schrödinger's equation we write h operating on psi is just the same thing as IH bar d by dt of psi. And so we identify that we can write down the Hamiltonian as this operator, IH bar d by dt. Now, if we take the time operator to be just t, we can work through this here. It's not quite clear that we really have a time operator in this quantum mechanics, so this is a little less rigorous from a mathematical and perhaps physical point of view, but nonetheless we can derive an uncertainty principle here, at least by analogy. Then, using essentially identical algebra as we just used for the momentum position uncertainty principle, then we can take the commutator of h and t for time, exactly the same algebra as I said, and we get IH bar, or technically IH bar times an identity operator. And that enables us to propose an uncertainty principle for energy and time, that is delta E times delta T is greater than or equal to h bar over 2. And that turns out to be a useful relation. It certainly works in the situations we typically look at. And this, of course, is very closely related to a frequency-time uncertainty principle that is quite rigorous in Fourier analysis. We would use actually mathematically an identical form of proof here to get this uncertainty principle in Fourier analysis, and we can get it by analogy at least from our energy-time uncertainty principle by noting the energy is h bar omega here, so therefore delta omega delta t is greater than or equal to half, just by taking the h bar out of both sides of our energy-time uncertainty principle. But quite rigorously, from a mathematical point of view, we can certainly derive this uncertainty principle in ordinary classical Fourier analysis.